Alright, today we're going to talk about Young's double slit experiment. This is a really amazing experiment that was conducted in 1801 by Thomas Young. And this experiment showed the wave nature of light. We're going to be looking at several different natures of light or models for light behavior, and this is the first one we're going to explore. Now you'll remember when we were just studying sound that we played a tone through two speakers and you walked around and you heard places where there was constructive interference and destructive interference. So the constructive interference occurred when troughs met troughs, crests met crests, you had a loud spot. And then destructive interference occurred when you had a crest, meaning a trough, and you would hear a soft spot. Well, the same thing happens with light. So if I take light and I shine it through a small slit, which makes basically a point source wave, then that wave is going to hit both of these slits at the same time. And so each of these slits is going to create a crest at the same time and a trough at the same time. Now notice that the light bends around the corner a little bit. That is called diffraction, and we will talk more about that later. So the waves travel towards the screen, and you'll notice there are places where crests are meeting crests and troughs are meeting troughs. And at those places, you're going to have constructive interference, which is where you see a bright spot on the screen. This is our screen here. The one in the center is the central maximum. So m equals 0 when you do your equations later. And then here, along this line, a crest is meeting a trough, and so there's destructive interference, which means that you're going to get a dark fringe right here. Now there's a pattern of light and dark fringes formed on the screen. You'll notice that they're equally spaced apart, and they should get dimmer as you go farther from the central maximum because the light is traveling farther, and so there's less energy there. So the first bright spot on either side of the central maximum is m equals 1, the second one is m equals 2, and so on. This is what it will look like when you shine your laser through your slit. Now I want you to notice that when we shine a laser through a single slit, you are going to get a central bright spot, and then you're going to get some dimmer spots on the sides. We'll talk about that later. But today we're going to focus on the double slit pattern. So the double slit pattern is these little teeny tiny bright spots and dark spots that are occurring. Let's talk about the geometry of this whole thing. So here's our picture. This is our screen, and we have the light traveling from slit 1, traveling along this path to the screen, and then slit 2 traveling along this path to the screen. Now, we know from our study of sound that constructive and destructive interference occurs because of a path length difference between the two waves. So R1, you can see the light coming from slit 1 has traveled less far than R2 here. Now, if I set up this triangle here, Y is going to be our position of the bright spot with relation to the central maximum. And then L is the distance between the slits and the screen. And we know that tan theta here is equal to Y over L. Now, in reality, the screen is much, much, much farther away than the slits are apart. So D here, which is the slit distance, is much, much smaller than L. And you'll see that when you get your double slit and you shine it onto a screen that's really far away. So what we're going to do is assume that these are parallel. So we can assume that these two rays, R1 and R2, are parallel, and we can make this little triangle right here and see that this distance right here is our path length difference, which we call delta R. And if we set up our triangle, we know that delta R is equal to d sine theta. We know that because of the trigonometry here with this picture. So we know that these are perpendicular to each other. This is theta. So that these two are alternate interior angles, and so we can see that our thetas are equal. I know I didn't explain that really well, but we have to keep moving, so you can pause it and look at it if you need to. Constructive interference occurs when the path length difference is a full multiple of the wavelength, and complete destructive interference occurs when the path length difference is an odd multiple of half the wavelength. This is just like it was with sound. Alright, so let's derive our equation. So we know constructive interference occurs when delta R is equal to a full multiple of the wavelength. And we know that delta R is d sine theta from our previous page. Now our theta is going to differ depending on what fringe we're at. So here is our center maximum. The first one is m equals 1. That's going to be theta 1. And then the second one is m equals 2, which will be theta 2. We're going to use the small angle approximation again. So small angle approximation says that tan theta is about equal to sine theta, which is about equal to theta, for angles less than 10 degrees or 0.1 radians. So we're going to take our sine theta out of there, and we'll have theta sub m equals m lambda over d. Now we also know that we can set up this triangle, which we already did on the previous page, but just to refresh, L is the distance between the slits and the screen, and y is the position of the bright fringe in relation to the central maximum, which would be right here. So ym equals L tan theta. We can solve, since tan theta is about equal to theta, we can solve for theta here. And we get theta equals ym over L. Then when we set these two equations equal to each other, we get ym over L equals m lambda over d, and we rearrange that for ym equals m lambda L over d. So this is the equation to tell you what the position of the bright fringe is from the central maximum. And if you put a 1 here, you'll get the first bright fringe on the top and the bottom. Second, 2, you'll get the second bright fringe, and so on. Lambda is the wavelength of the light, L is the distance between the slits and the screen, and D is the distance between the slits. Now, we also know that if our we will get destructive interference if our path length difference is equal to wavelength times m plus 1/2. So this is an odd multiple of half the wavelength. If you put a 0 here, you'll get 1/2. If you put a 1, you get 1 1/2. If you put 2, you get 2 1/2, and so on. So this will this will occur, when this occurs, you'll get dark fringe. So this equation tells us the position of the dark fringes on the screen. And that is a short intro into Young's double slit experiment.